let's quickly go through the basics of CNN. So we need to first understand the format of image which will be used. And by now, I think all of you should know that it will be in a matrix format. If it's a grayscale image, two-dimensional array. If it's a RGB colored image, it will be three-dimensional array. All right. So that will be the input right over here. And this is a general CNN architecture we discussed in the last lecture. The input is like some n-dimensional data in form of a matrix. And this will be your CNN network. You will have certain layers in this network. We are going through going to go through all these layers today. And then finally, you will have a final layer which will give you predictions, what this network thinks about this input image over here. So that's very general architecture which will be used like in most of the problems you solve. And so what we're going to use today to understand this CNN is filtering. So filtering, I can quickly go over this, but again, we recently covered this in one of our lectures, so I don't think there should be any doubt. So filtering is simply you have a kernel, and then you have an image patch. You take element-wise multiplication, and then just add those values, and that will be the output of your filtering operation. Okay, so it's just like a linear combination of the neighborhood pixels. So this picture of filtering, I think, will be very useful if you try to understand this. So it's just a linear combination of neighboring pixels, right? So trying to learn local features or local patterns in your input data. So that's the correlation. So there's the input patch, again, the kernel. You just do linear combination of this and change the value at this pixel location. And this we can do using two things, like we can use a correlation, and this is the equation right here. This is again similar to what we discussed in the last slide. And the other thing you can use is like convolution. And again, this is almost similar to correlation. And I think we're talking about that question, right, from homework assignment 3, I think. So that's the only difference. In this case, you have these negative signs in your kernel, which means that you are flipping your kernel in X direction as well as in Y direction. And then you can use the exact operation which you use for correlation. So this H is your original filter for convolution. If you flip in H direction, you will get something like this. If you flip in Y direction, you will get something like this. Then you can directly compute the correlation, and the output is going to be convolution of this function using this kernel. So okay, so that's fine. And then we also saw how we can use smoothing as well as computing derivatives. So this is like combination of both, right? And then how this operator can actually detect edges in your input image. So X derivative is going to give you vertical edges, Y derivative is going to give you horizontal edges, which means that this is trying to find some kind of patterns in your input data, this filtering operation. And in this case, that pattern is just edge. So this is interesting because what you can do is if you change your filter, and that might help you in detecting other patterns in your image. And that's like the main motivation, or you can say the main intuition behind CNNs. We try to learn these kernels, different kernels, and all those kernels try to find like different patterns which they are like meant to find in the input image. And then you can actually extract meaningful features or information from your input data. So that's the main motivation or intuition behind your CNN architectures. Okay, so MLP, I think this is fine. This was just last lecture. So you will have this set of neurons and stacked on top of each other. You can have multiple layers, and you take a feature vector here as input, and you make some predictions. So you can have one prediction or you can have multiple predictions. This is also called feed forward network. So we also talked about this learning phase, right, where we are saying that, okay, you'll have this training data, you will have all these images, and you will extract features from these images, and then you will perform training. So usually, like in classical computer vision, what you do is you first extract features, and then you train your classifier. But using deep learning, when you're using CNNs, so as I said, you try to learn those kernels, and those kernels can automatically extract features for you. So we don't need this additional step. This all can be done in like single step, where we can plug in our convolutional neural network and directly feed this image in, and those networks will be able to extract meaningful features and also perform the task. So if it's classification, they will be able to classify that image. Okay, so this is called end-to-end learning. You might have heard this phrase a lot. And this is called end-to-end learning because essentially you are just doing a single step. You have this network, you can treat this as a black box, and we don't have to understand what it's doing, but it's solving the problem. And it's called black box because we are just feeding in data here. So a bunch of images and it's giving you output. But how it's actually making those inferences to predict or to make those predictions, that's not entirely clear. It's very hard to understand that. That's the reason it's called a black box. And that's also the reason it's called end-to-end learning, because you're just combining everything from feature extraction to classification in just one single step. Now you can compare like neural networks with CNN. I think briefly covered this in the last lecture as well. And the reason why we need CNNs was if we directly use pixel values as features. So as we have high dimensional images, it will be very difficult to fit that into memory because we'll need a lot of weights for that. And that's why we need CNN. So that's one reason. The other reason is like using pixels as features is not, it's not a good idea because they don't give you like a lot of meaningful information. Okay, so now let's try to understand what's the fundamental operation in your convolutional neural network. And you already know that we have been talking about that a lot in previous lectures. So it's called convolution, and later we'll see that it could be correlation as well. And that's like the core building block of a CNN. And how it helps you like save memory is you can use this convolution operation in your input data, and you can also preserve the structure of your image. Okay, so let me describe what that means. So let's say you have an image, and in this case we have 32 cross 32. So that's the resolution, height and width, and then 3 is for channels. All right, so this is colored image. We'll have 3 channels R, G, and B in this dimension, and then the resolution is 32 cross 32. Then what you do is you take a filter, something like this, and let's say the shape of the filter is 3 cross 3 cross 3. Then you perform convolution of this filter on this input data, and this is like similar to what you did for filtering. You take this kernel or this filter and apply it at like all the possible locations in this input image. All right. So this filter is convolved with the image, and what will happen is when you put this kernel, let's say at any location in this input volume. So after the convolution operation, and that will be linear combination of the values of this filter, and the weights will be like the values in the image patch. And at the end, it's just going to give you one number. All right. So one filter applying at one location will give you just one number. Now, of course, what you can do is you can apply like the same operation at different locations. So depending upon how many locations you can put your filter, you will get that many numbers as output. So let's try to understand that and try to visualize it. So if you convolve all the spatial locations in this input data, so you will get something like this. And you can see here that the depth is just 1, because for each location, you will just get one value, all right? And then the X and Y extent of this is like when you change the X and Y location of this filter in this input map. So you can see that the input resolution was 32 cross 32 cross 3, and the output map is 30 cross 30 cross 1. So we will talk about like this, how we can get this number 30, how to derive this. We have a formula for that. But this number 1, I think it should be fairly easy to understand. You just have one kernel. So you put at this location, so it's going to give you just one number. So that's why the depth is reduced to 1. So this is called like the feature map or the activation map when you apply this filter on the input. Okay. Now what you can do is, and again, this is just one filter. All right. What you can do is you can take another filter, and again, you can repeat the same process. You can take that filter and again, like run it through the whole image again. And what's going to happen is you will get like another activation map which will have the same resolution as this. Okay? So you have two kernels, you get two activation maps. So you can see that depending upon how many kernels or how many filters you use, that will determine what will be the depth of this activation map. All right, so that part should be clear. So we are clear about like the depth of these activation feature maps. So there is just one point I will come to that in a bit. But regarding these dimensions 30 and 30, so these dimensions will depend upon the resolution of your input feature map and the size of your kernel. All right, and we'll talk about that in a bit. Okay, so I think there is a question from LG. No matter how many filters, all are applied to the original image. Yes, that's true. So in this case, it's image, but later we'll see that when these could be activation maps as well. So you can use as many filters as you want and apply on this feature map. All right. So if it's still not clear, just hold on. I think in next couple of slides, I think your doubt will be clear. And if it's not, then we can discuss, come back to this again. Okay. So another question from Fernando, if not specified, should we assume no padding for future quizzes? Yeah, we haven't talked about padding yet. We'll come to that. So don't worry about padding and quizzes. So in quiz, we will only ask like when we have covered that topic. Okay, so whenever you develop a new CNN or a convolutional neural network, so similar to neural network where you have layers, and each layer just represented like how many neurons you have in that layer. Similarly, in convolutional neural networks, we have the concept of layer. And in case of CNN, one convolution layer will just indicate like how many kernels you have and what is the shape of those kernels. So there is some analogy between this and neural network, right? There is like how many neurons you have. This is how many kernels you have. In case of neurons, you don't care because it doesn't have any shape or something, right? It's just one neuron. But in case of kernels, it could have some shape. So this is like one additional bit of information. So once you have this, this represents like your entire convolution layer. So let's try to visualize this again. So again, this is your input image. 32 cross 32, 3 channels, which means it could be an RGB image. And then you can have one convolution layer, which is represented by 6 kernels. And the shape of the kernel is 3 cross 3 cross 3. And after this convolution layer, which means like applying these kernels on this input image, you are going to get this feature volume, which will have this resolution, 6 cross 30 cross 30. Okay, so you can see that the depth is 6. The reason is you had 6 kernels. Okay, so let me cover one important point here. So you might be seeing like the shape of this kernel. It's not 2D kernel, it's 3D kernel, right? But we say we are performing 2D convolution, but essentially, if you think about this, this is a 3D kernel, and the actual operation which you are doing, it's 3D convolution. So in this case, you can see here that you have 3 dimensions. So the first 2 dimension 3 cross 3, they are for like the X and Y in 2-dimensional space. The third dimension, which is 3 here, it should always match with the depth of your input feature map. Okay. So that could be confusing, but just try to learn that whatever the depth is, in this case, it's 3. So your depth of the kernel will always be 3. Okay. So essentially, it's like 3D convolution, not 2D convolution. But in depth, we don't stride it, right? It's just one location. So essentially, the operation is 3D, but at the end, we are just performing 2D convolution because only 3 cross 3 kernel is being applied at different locations here. Okay, so I think there's a question from Mustafa. Can't we apply 3 2D convolutions in every dimension? Yes, you can do that, right? You can do that, and if you just add those values, and if the values in the kernel are normalized, it will be essentially like similar what we're doing here. using a 3x3x3 kernel. So depending upon like what your kernels are and how you process the output, it could mean different things. For example, if your kernels are not normalized, or you treat like those three outputs as like three different activations, then that's essentially like 2D convolution, and I mean three separate 2D convolutions, or you can say that three separate filters you're using. Okay, so another question from Curtis. So I could do a 5x5x3 in this example. Yes, that will be a perfect kernel to use here. You can use a 5x5x3, you can use a 7x7x3. So the third dimension should match with the depth. That's the only constraint. Okay, so this is your one convolution layer in your CNN. So that's pretty simple, right? There's nothing new information here. You already knew that. Now, a deeper convolutional neural network, again, it's pretty simple. You just stack like those convolution layers on top of each other, and that will build your convolutional neural network. So that's it's a very trivial extension. So in this case, you can see that this is the input image, again the same resolution, same depth. This is the first convolution layer, and again we are using 6 filters of this resolution, so you get a depth of 6, and the resolution reduces to 28 cross 28 from 32. And this is the second layer. In this case, you're using 16 filters. And again, the shape is 5x5x6. So make a note of this, like the depth is matching here, right? 6 with 6. And you're using 16 filters. Therefore, the depth of the next activation map will be 16. And similarly, like you can stack like these kernels on top of each other. So this will be your deep convolution neural network. So it's just like sequence of these layers. Question from Daniel. So this is technically 3D convolution, but we are doing 2D convolution. So we are saying it's 2D convolution, but technically it's 3D. I think if that's not confusing. But whenever you say it's a 2D convolution or a 2D CNN, this is exactly what is going like behind the walls. Was that clear, Daniel?
Yeah, so if we had 3D image input, like actual like three-dimensional image, then we'd technically be doing 4D convolution, right?
Right, exactly. That's true. That's a good point. So there we are doing 4D. So your kernel will be like 4-dimensional in shape. Okay, so another question from Rajat. How does sliding a same single 3x3 filter over entire region of an image make sense if different regions of an image contain different objects and their feature representations might be different? So that's a very good point. And so the idea is we don't expect one filter to extract all the features. One filter is only responsible for extracting certain type of features. All right. So for example, when we were talking about edge detection, right? So we had like a derivative operator, and the task was just to detect where there is a vertical edge or not. So there could be some other features, but if you totally ignore it, it will only detect vertical edges. So one filter is tasked with one kind of pattern, and you are right that different part or different regions of the image might have different patterns, which is fine. So if that pattern is present, it will give you some value. If not, then it will just ignore it. And that's the reason we need multiple filters, right? So that's why we have 6 different filters. So it could be like one filter is detecting horizontal edge, the other filter might be detecting vertical edge, the third might be detecting like slant edges. Okay. So I hope that is clear now. Another question from Carlos: why do we end up with 28 the first time and 24 the second time? Yeah, we are. That's a very good question, Carlos. We are going to talk about that. So that's a very good observation. Okay, so you can see that the resolution of your feature maps it's actually reducing. So going from 32 to 28, 24, and it might go further down if you stack more convolution layers here. Okay, so Now let's talk about parameters. So we talked about parameters when we were talking about neural networks as well. So there it were just like the weights in your neurons. In this case, again, these are just the filters you are using, and I think there will be a pop quiz on this, I think, after a couple of slides. So try to understand this very carefully. So when you have an input image, let's say 32 cross 32 cross 3, and you're using a 3 cross 3 cross 3 filter. So as Rajat mentioned, that you apply the same filter at all the locations, which means that you just need these many numbers or these many parameters actually for this operation. Okay. So the parameters are, so this is the input image, and this is not like, this will not count towards parameters because this is your data. Parameter is something which you are going to learn in your network, and those are going to be your filters, and these are the parameters. So in this case, these 3 cross 3 cross 3, these 27 values will be parameters for this particular filter. And depending upon how many filters you use, you can just count the dimensions or the values which are stored in a filter. They will count towards your parameter. So in this case, for this convolution layer, if you only use one filter, then you have 27 different parameters, right? And in this case, you can see that again, we are using 6 different kernels. And if the shape is 3 cross 3 cross 3, you can multiply 27 with 6. That will be like the total number of parameters you have in your network or in this particular layer. So it will be 6 times 3 cross 3 cross 3. So this kernel is here 3 cross 3 cross 3. Okay, so now let's try to understand, like when we are performing convolution, we have seen that this filtering, correlation, convolution, whatever we say, this is trying to find some kind of patterns in your input image. And let's try to understand what exactly is happening when you convolve like two different functions. So one will be like patch from your input image, and the second will be like your filter itself. And let's see, let's say this is your function f. This is just like a step function. And let's say this is your kernel. So when you apply convolution, or when you convolve these two functions, what's going to happen is you flip this function, right? So in this case, it's symmetrical, so it's not going to change. Then what will happen is you apply this kernel at all the possible locations in this function. So in this function, there will be negative infinity towards left, and then positive infinity towards right. And it's this plot is actually showing that. So the blue line over here, this is the function ft, and the red one, which is actually sliding, is your kernel. And what we are doing is we are trying to apply this kernel at all the possible locations, starting from this -2 and all the way up to 2. You can actually apply beyond -2 as well, which is perfectly fine. We are just not showing it here. So what will happen is when you apply this red kernel, let's say at this location, so the response is going to be 0 because there is no overlap between your kernel and function. Right? So if the values in the function are 0, then because this is element-wise multiplication, so the resultant, the linear combination, is going to be 0. And you can see, you can try to observe this black line if it's visible. Right, so this black line is the response of that convolution operation. And you can see that starting from the left, it's 0 because there is no overlap. And as soon as you reach -1, you can see that there is like the kernel is going to like be overlapping after this point. You can see. Okay, so this yellow region is the overlap. And as you move towards right, the overlap is going to be like higher and higher. The yellow region is growing, and that's the response, this black one. So as the overlap is growing, which means that the signals and the function and the filter, they are like more similar. So the response is growing. And at the center 0, you can see that they're perfectly overlapping, which means that your function is exactly same as your kernel. And you can see that then you're getting the highest response. So this black value is like close to 1. That's the maximum response you can get. And as you move towards right, again, the overlap is going down because the signals are kind of dissimilar then, and then it goes to 0. And then it will remain 0 because there is no overlap. So this is like the response from the convolution of two different functions. And what the takeaway from this is, when the function and the kernel are perfectly overlapping, or they represent the same pattern or the same shape, then the response will be very high. If they don't match at all, the response will be 0. And if there is some overlap or there is some similarity between these two functions, then there will be like some response or activation somewhere in between. Okay, so that's the takeaway from this. And right now, this is just step function, but this is true for any complex pattern or any complex function. All right, that's how convolution works. So then you can see that what's going to happen is when you apply a kernel to your input image map, so if you find that particular pattern, you are going to get a very high activation. So then essentially your convolution operation is just doing pattern matching. If the pattern matches with the kernel, it's high activation. If it doesn't, it's a low activation. Okay, so that's the equation for, so it's like continuous convolution, but again, that's fine. I'll just explain how this works. Okay, so again, this was a 1D convolution, but you can easily extend this to like 2D convolutions, where you will have not just like X dimension, we'll have X and Y. So the same thing was happening when we were trying to do edge detection using your derivative operator. So if you look carefully, so this is a combination of derivative and smoothing, but just ignore 2. You will have 1 over here, right, as a derivative operator. So if you carefully look at this operator, this represents a vertical edge, because you have 1 in the left column, then it goes to 0, then it's again goes to -1. So this is kind of showing an edge, right? So then what will happen is, if you perform filtering using this, then your filtering operation is just trying to find this pattern in your input data. And if it can find, it will give high activation. And that's why we were able to actually detect edges using these two operators. Okay, of course, those were edge detection, but we can, as I said, we can use any other pattern. We can have any other complex pattern as well. I think there is a question from Mehdi. How can we get from 3 channels to 1 channel? Okay, so let me go back. All right. So your filter is 3 cross 3 cross 3, right? When you place it at like any location, you can see that you're totally covering the depth, and that's the reason like the depth should actually match with the third dimension. So when you place this filter at this location, you find the weighted average, right? Or the linear combination. So this patch on the input image will have 9 values, right? 3 in the depth, and then 3 and 3 in the X and Y axis. And again, you will have 9 values in this kernel. So you just take a linear combination of these two, and that's going to give you 1 number. So if it's just 1 number for this location, for all the locations, again, it will be 1 number. And that's why like this is this activation map showing here, right? So because it was just 1 number along the depth, so that's why it's reducing from 3 to 1. Is it clear, Mandy? Okay, great. Okay, so now let's try to look at this demo. This is your input image, and these values are like the pixel values. So this is kind of a binary image, and this is your filter, and you can see that this is 5 cross 5. This is 3 cross 3, and the depth is 1. So again, the depth of the filter is also 1. So we are just ignoring that. Now, the way you will perform convolution is you will take your filter, put at all the possible locations, slide it across the input image. So the first possible location is this one, right? And you just compute the element-wise multiplication, add those values. That's going to give you 4. Then you can shift your filter to this location, Again, you can do the same element wise multiplication. That's going to be 3, and you can do that for like all the possible locations, right? So this one, then the next will be the center, then on the right. Now you can see that the resolution of the input was 5x5, filter size was 3x3, and your output feature map is again 3x3. So it reduced from 5x5 to 3x3. And one interesting, so that's one thing. And the other thing is you can see that, let me actually go back. So the pattern in your input image, these are all 0. So this is kind of the upper diagonal, right? All ones. And in this case, this is kind of a cross. So you can see that whenever you are getting like a pattern which is closely matching with the cross, that will give a higher value as compared to other locations. Okay, so you can see that whenever you are getting a 3, it's not close to the cross over here. But whenever you have like all diagonal one, you get a 4. Okay, so it's kind of pattern matching. Okay, so let's try to understand that like using some maybe a little more complex example. Okay, so let's say this is your kernel. So you can have patterns in your kernel as well, right? So this is a 5x5 kernel. And if you represent this using like discrete values, then you can represent it something like this. So if you just follow these all ones, so this represents like this shape. Okay. Now let's say we have an input image, something like this, a triangle. Now we want to apply that filter, which I just showed you in the previous slide at this location. So ideally what should happen? I mean, that pattern is exactly matching with this pattern, right? So we should get like a very high activation. And let's try to do the maths here. So this is the kernel, right? That's the kernel. This is like patched from the input image. And you can see that your kernel was exactly the same, right? Now, if you perform filtering of this kernel on this image patch, which is shown over here, you can do the math. It's going to give you like a number 5, because all the 5 positions will perfectly match and you will get 1 for each location. So just sum those up, it's going to give you 5. Okay, so that's high activation. Now let's try to put the same kernel at a different location on this input image. In this case, let's say this corner over here. Now you can see that the kernel is actually not quite similar to what we are seeing here in this image patch. So this image patch is something like this. And if you try to binarize this or create a discrete matrix for this, it will be something like this. So if you just follow these ones over here, so that's a L shaped coming from here, right? And then this is your filter, original filter. And again, you can do the convolution, do element wise multiplication. It's going to give you 1, because I think only one of the locations will have a match. I think this one, right? All the other locations, it's not matching. So which means that you get a very high activation when the pattern in your input image was matching with the pattern in your kernel. And if it's not matching, you are getting very low value. So this somehow like gives you an idea like what exactly you are learning when you are extracting those feature maps. So those feature maps represent like if they have high value, it means there was a perfect pattern matching like done in your input image with the kernel. And if it's like all close to 0, it means that you were not able to find any meaningful pattern in your input data. Okay. And that's why they are actually called activation maps, because it's kind of giving you activation whether there was a match or not. So again, as I said, I think there was a question from Rajat, why we use just one kernel for all the locations, because we might have different patterns at different regions of the image, and that's true. And that's the reason we actually use multiple filters. So one filter might be just trying to match like the top of the triangle. Some might be like that L shape of that triangle. Right? So that's why we need multiple filters. And again, so this is showing you a demo. Like, so this is your input image. And sorry, it's going pretty fast. So if you look at that kernel, so this green one is a slant edge towards right. Okay, and the second time the red kernel is again a slant edge towards your left. So these two are your kernels, and you can see that when you run the green one, the edges you are getting, those are the edges which are actually towards the right. And again, similar like the second one, all the edges which are towards the left. Okay, so again, just showing the same thing.
Professor.
Yes.
So if the goal of a convolutional neural network is to learn the kernels, so when we start like the training, like is it beneficial to have like a strong initial guess to what the kernel might be?
Yeah, that's a good point, but I don't think we should discuss that now because we haven't talked about like convolution like fully. Then we will talk about like how we train our networks, right? Then I think we should be worried about like network initialization and all of that. But if you have experience, I can quickly give you like one sentence answer to that. That's true. If you have a very good initialization to your kernels, then it helps your training a lot. Okay, so that's like related to using pre-trained weights in your network.
Okay.
Okay, all right. So now there was a question earlier, like how we went from like 32 to 28 and then 28 to 24. Okay, so let's try to understand all those dimensions. Now let's say you have a input image map of 7 cross 7 and you're using a kernel of shape 3 cross 3. Okay, so the filter is 3 cross 3. So the first position you can apply is like this, then you can move towards right. Now you can see that you start from this location, and this is like again related to what we learned in filtering. And there was a comment about padding, so now is the right time if you still are confused about padding once we are done with this. So this is the first location, then second, third, fourth, and fifth. So you can see that the resolution of input map was 7, like along this axis, but there are only 5 possible locations where I can put my kernel. And you know that for each position, when you put your kernel, you get one value. So that will define the resolution of your output activation map. So you can see that because there are only 5 possible values, in that dimension, you are only getting 5 different values, right? Similarly, like the vertical one as well, you will only get 5. So then this has something to do with what was your original resolution. So in this case, it's 7, because if it's 7, that will define like how many positions you can put it in. The second important factor is the filter, which is 3 cross 3, because if your filter were like just 1 cross 1, then you could have started from the first location over here, and that might have given you 7 different positions. Similarly, if you increase your filter size, let's say it goes to 5 cross 5, then you will not be able to start until like this point. This will be your first location, right? So it depends upon what's your resolution of input image and what's the shape of your filter. So we can actually easily come up with a formula for that. It's pretty trivial. You can just take so n here represents the length of like this input image or feature map in x dimension. So one thing you will notice is that sometimes I will say input image, sometimes I will say feature map, because essentially you're applying these kernels on a volume, right? And that volume could be your image, the input, if it's the first layer. But again, you can do the same operation like in your intermediate layers where you will have activation maps. Okay, so I might use that interchangeably, but that's perfectly fine. So n is like the size of the input. In this case, it's 7, and f is the size of the filter. In this case, it's 3. So if you put in this formula, that's going to give you 5. And of course, this is like a square shaped activation map. This is a square shaped filter. You can have an odd shaped filter as well. So this could be like 7 cross 9 as well. And this could be 3 cross 5 as well. And although we don't do that, but theoretically it's possible. So that's why when we're computing these dimensions, these are like, we compute these independently for each axis. Okay. So that's a very simple formula. Let's try to make it more complicated. So now the next concept is like stride. And stride is something, what if we don't want to apply like the filter at all the possible locations, because we might want to save some computation power, or we might think that if we just shift by 1 pixel, it's not changing a lot. We are still getting the same activation. Okay, so those could be the reasons, and that's why we need stride. And stride is something like the amount by which you shift your filter in each direction, right? For example, the example I showed you in the previous slide, the stride was 1. We were not skipping any pixel. But what we can do is we can try to skip pixels in between. So let's say if the stride is 2, then what we'll do is we will skip actually 1 pixel in between. So the step is actually 2. So if I say stride is 2, it doesn't mean like how many pixels we are missing. It says what will be the step size of your filter. Okay. So in this case, if stride is 2, we are only skipping 1 pixel in between. So then this is the first location if the filter is 3 cross 3. And if the stride is 2, this is going to be the second location, right? We skip this pixel. So you can see that the step is actually 2, 1 and 2. Then the next will be at this location. So then you can see that if we use a stride, then you will have to update your formula, because the activation map size in this case, you can see that it's just going to be 3 cross 3 because there are only fewer locations to put your kernel on the feature map, right? So then again, we can update our formula. So if we are using a stride of S, we can say that it will be n minus f, then we divide that with the stride and then add this one. That is going to give you the output size. Okay, so we have a pop quiz. Any question until this point? Okay, that's good. So the question is pretty simple. Let's say you have an input feature map 7 cross 7. And let's say we are using a filter of 5 cross 5. And we are applying this filter with a stride of 1. The question is, what will be the resolution or the size of the activation map after this filtering operation? Okay, so you can take like 30 to 45 seconds and just send me like a direct message. I think we have a lot of answers. Most of them are correct. Few of them are incorrect. Okay, let me. Okay, so you can directly use that formula like which I just showed you. So the activation map size will be 3 cross 3 because it will have like 3 different locations, right? These 3, and then these 3, and then these 3. Then you can put your 5 cross 5 filter. So that's good. Okay, so that was the first concept, which is very important when you perform convolution. The second is stride. Okay, so I think, yeah, we just covered stride. So some more variations. So let's try to understand if there can be any complications. So in this case, we have a 7 cross 7 map and we have a 3 cross 3 filter, and we want to apply this filter with a stride of 3. So this is the first location, then we skip 2, go to this location, perfectly fine. But now if you do a skip of 2, you will see that you are going out of the feature map. Okay, so you can't put like this kernel in any next position. And so then what's happening is you're kind of ignoring these 3 pixel values from your input data, which is kind of bad. We don't want to do that because each pixel value is important, right? This means that not all combinations of your activation map, filter size, and stride will be meaningful. Okay. So you'll have to be very careful when you design your network, when you are coming up with the like shape of your filters when you're defining like what should this stride. You can't just pick like any numbers and put it together and it's going to work. So I think a good thing is like you can use that formula if you're not sure of what the shape is going to be, and then make sure that it fits perfectly. Okay, so then what's the ground rule? So the ground rule is if we use a formula which we just discussed and put all these numbers, the size of the activation map, the size of the filter, and then the stride you're going to use, and then that will give you some result like what's going to be the size of the output feature map. So in this case, you can see 7, 3, which is fine, and then stride of 1. So that's 5, perfectly fine, no issues there. If you use a stride of 2, you're getting a 3, that's perfectly fine. But if you use a stride of 3, then it's not a integer, it's 2.33, and that's odd. So if you don't get an integer, then it means that that combination is not going to work. Okay, so it's one simple trick which you can use. Now, another important concept is padding. So padding usually, we have seen like there are different ways to do padding. I think in when we were doing filtering, right? So it's almost similar, and mostly we just perform zero padding, and it just works perfectly fine. And even like when we are doing filtering, we saw that we can have different kind of paddings, but at the end the results were not that different. I mean almost all of them were like almost similar, right? It was not having any effect. So similarly, like you can have different kind of padding, but as they work like quite similar, so we just use zero padding. Now what padding means is, let's say if you have a feature map here, again this is a revision, we have covered this earlier as well. So in this case it's a 7x7 feature map. And when I say that we perform a zero padding of 1, which means that in each direction or each borders, you just add like values of 0. Okay, so in all the 4 directions, you're just adding 0. So this is 2 dimension. If you will have 3 dimension, again, you will have to do padding in all the dimensions. All right? And again, you can have padding of 2. In this case, you will have 2 columns of 0 or 2 rows of 0 in all the sides. So that's called padding. Now let's try to understand how this padding is going to change like the resolution which you're going to get for your output activation map. In this case, the input feature map is 7x7. Let's say we want to use 3x3 filter. So earlier, this was the first possible location, right? But after padding, you can see that we can directly start from the first pixel location. So we are not ignoring any pixel value from your input feature map. So that's a good thing. And that's like one motivation why we want to use padding. And then you can see that you will be able to apply this kernel at all the possible locations in your input feature map. And that's only because of this padding. And therefore, what you're doing is you are essentially preserving the shape of your input feature map. So the input was 7x7, output is also 7x7. And there are certain applications or certain problems where you want this quality, where you don't want to reduce the size or the resolution of a feature map if you want to preserve it. So this is something which you should know, padding and stride. Now, usually the most common thing when you want to do that preservation, what we do is we use a stride of 1, and we also use a padding of 1. So if you use a padding of 1, then the kernel shape should be 3x3. So what we can do is we can actually try to figure out the size of a kernel if you want to preserve the resolution, right? So this is the same equation which we had, and this is going to give you like the size of the output feature map, right? So we want to preserve it, that's why it should also be n. N is like the size of your input feature map, and you can just solve this equation. That's going to give you like whatever parameter you want to put. So of course we'll have to make some assumptions, like maybe if you want to put stride 1, so replace that with 1. So this is going to give you padding. So this is the simple formula for padding and your filter size. You can play around with those two. Okay, so that's good. Now another interesting operation is pooling. So pooling is also like earlier I showed you a very general architecture of CNN, and there was like a layer which is like subsampling layer. So in subsampling layer, we actually perform pooling. And pooling means there are different reasons why we use pooling. The first reason is when we want to save some memory and we want to reduce like the resolution of your input data as we move deeper into your network, then we can use pooling. That's motivation number one. The second motivation is when you perform pooling, it actually makes your network or whatever algorithm you're learning invariance to small translations of the input. And we'll see like how it does that. So I think there is a question from Anshuman. If my required pattern is near border and my kernel was a perfect match, but because of zero padding and stride not equals to 1, my activation will go down. Thus, does this affect an overall result? Okay, so first of all, there are a couple of things here, right? So if you are talking about CNN, then this doesn't apply because you cannot say that your kernel was perfect match because you don't define your kernel will be learned, and whatever stride, whatever padding you use, then to match that particular pattern, like in your border, your network will automatically learn like what kernel is required. But like from other point of view, if you're talking like in general filtering, if you already know your kernel, then I think this is true. It's going to affect the result. Okay. Right, so let's try to understand what pooling is. In pooling, you have, let's say, this activation map. So this is a 4x4. And what we want to do is we want to reduce the shape of this feature map. So let's say we want to reduce it to 2x2, something like this. Okay, so from 4x4 to 2x2. And again, so what will happen is you will have to define like some kind of shape for your kernel. Okay, so in this case, the shape is 2x2. And in this case, the stride is again 2, right? Both in X and Y direction. And this is called like max pooling kernel, but this kernel, it doesn't like, there's no learning involved in this kernel. What it does is it will directly pick like the maximum value in this particular region. If it's max pooling, of course, we can have different kind of pooling. We can have max, we can have average, we can have median pooling as well. Like we had median filtering, right? So if this is max pooling, then we are going to pick the maximum activation. So in this case, it's 20. So we pick 20 and put it here. Similarly, we pick like the maximum activation here, 30, we put it here. So 112 and then 37. So your input activation map is reduced to like just 2x2 using max pooling. And again, if you perform average pooling, this will be the result. We are not going to go through because we just compute the average and replace the value. So if you now think about this, if you look at, let's say, this particular activation map, so these numbers are actually giving you whether you were able to find any particular pattern in your input data or not. And if it's giving you 30, it means there was some kind of match. 0 means there wasn't any match. So at this location, you couldn't find it. At this location, you could. But when you perform max pooling, you reduce like all of these 4 regions into 1, right? And this region is saying you were able to find the pattern. And this region actually corresponds to all these 4 locations. So what this means is it doesn't matter where that pattern was present in your input image. It would have been at this location. It would have been at this location. Still, we will be able to recognize it because of this max pooling operation. Okay, and that's the reason max pooling helps like to make your network translation invariant. Right? So you can translate your input pattern in this local vicinity, but still your network will be able to recognize it. So yeah, it makes representation smaller, saves memory. That's good. And the other interesting thing is you don't have to worry about like the depth here, because the activation, like the the filter is applied independently because you're just pooling like those regions, right? So let me show you one quick example here. So in this case, this is a feature map of 224 cross 224 and the depth is 64. So in CNN, we actually treat the whole depth at once, right? The depth of your kernel is also similar. But in this case, we treat all of these channels independently. So we will pick one channel, 224, 224, and then perform that max pooling operation. Let's say we reduce it by half. So this will become 112, 112, and we put it back at the same location. And you can see that the depth is actually not changing. So if you have 64 different type of patterns here, like the depth is 64, then that's being preserved here. So the pooling is only like on each activation independently. Okay, so as I said, I mean, you will have some kernel size, which will determine like what will be the output size or how much reduction you want in your input. And again, you will have stride like you had in CNNs. So in this case, you can see that your max pooling, the filter size is 2 cross 2, right? And stride is also 2. Because you put the filter here, then you move 2 pixels, put it here. Then again, in y-axis, you move by 2 pixels, and you get a 2 cross 2. I think there is a question from Fernando. For max pooling, is it uncommon to use filters bigger than 3 cross 3? Yeah, usually we use 2 cross 2 because if you reduce like your activation map by more than half, that's a lot of reduction. So we don't want to lose that much information in just one step. So mostly you will see like 2 cross 2 and a stride of 2. That's the most common you will use. But of course, no one is stopping you to use bigger filters. But later we'll realize, in terms of performance, that's not very efficient. Okay, so that's pooling. Let's do a quick pop quiz, and then I think we can end it here. So the question is, you have an input feature map. The shape of that feature map is 112, 112, and the depth is 16, right? Then you want to perform max pooling. In this case, the kernel size is 3 cross 3, and you're using a stride of 2. All right, the question is how many parameters are required for this particular max pooling operation? So there's an answer which is in floats. How can you have number of parameters in float? That's quite odd, right? Probably that's a typo. Another float. Interesting. Okay. So let me actually go back before showing you the answer. Most of you were correct. So that's good. So if you think about like what's happening, so this is a max pool layer, right? You have a 2 cross 2 filter, stride of 2, and this is your input feature map. And what you're doing here is you are taking like all these values. If it's a max pool, then you just pick the maximum value, 6 to 6. So now think about like what kind of weights you need for this, or do you really need weights for this? Because you're just copying these values. So in this case, you already know it's 8. So you just copy at 8. So all it requires is like maybe a sorting operation. Okay, so the answer is, I mean, you don't need any parameters, because max pooling is you just pick the maximum activation value. You don't need weights for that. So the answer is 0. I think most of you answered correctly. So I think that's all. We can end it here. I have a very small portion to cover where we'll try to go through that AlexNet architecture and try to understand like how the network parameter affects like the design of your architecture, and where it's like most of the memory is being utilized. And that's a very short portion. Probably we'll cover in the next lecture on Tuesday. And then we will move on to how we actually train these networks, because so far we have just studied like the basics, what is actually happening inside the network. And the next step will be to training this, and then we will see some like tutorial on PyTorch, how we can implement these architectures, and then that will be useful for your programming assignment 1, the second question. So if you have any questions, please go ahead. Okay, so question from Brian. Can you explain pop quiz answer again? All right, so let me go back. So the question was, so this is like, we don't care like what the size is, what the shape of your max pool kernel. So the question was, you have this max pooling kernel. So how many parameters are required? And for max pooling, as I said, we don't need any parameters, because in max pooling operation, all what we do is we just find the maximum value and then just store that value in the next activation map. So there is no transformation, no linear combination happening, for which weights were actually required. What happens in filtering operation? In this case, no such operation is being done, so no weights are required. So Brian, I hope that's clear. Question from Brandon. Max pooling makes the number of parameters to 0. Yes, you don't need any parameters in your max pooling layer. Question from Shivani. Was the pop quiz graded? If yes, how will we get the scores? So the scores, I think, should be, I think he graded that tau. I'm not sure whether he has updated like it in the web courses, but he should do that soon. I will let him know. Okay, so that's your first question. And but if you are eager, I mean, you can just drop him an email, copy me, and he will share the score with you. Okay. How is the midterm going to be? MCQ, short answers, programming. So midterm will be you will have a variation, lot of variation. Like you will have questions like you are receiving in your homeworks. So true, false, then multiple choice. You will have fill in the blanks. Then there will be some analytical questions asking you to like find the answer, maybe do some solutions, and maybe some description. So a mix of all these. Okay, so Shivani, I hope I answered both your questions. Brandon, okay. Brandon, was the answer for the first pop quiz 3x3? Yes, that was 3x3. Question from Matthias. Just to clarify, the pop quiz is bonus. Yes, it's bonus. So it's like top on 100%. Whatever grade you get, these scores will be added on top of it. So any last minute question before we end? Yeah, I think we are already over time. So let's end it here, and let me know if you have any further question. Okay. So question, I think from Ruchia, will the pop quiz be present after every lecture? I have to miss some last lectures because I have other subject midterm exams. Yeah, so I mean, it might be, sometimes you might see like multiple pop quizzes, sometimes there won't be any pop quizzes. It depends upon like the content of the lecture. Okay. Question from was the quiz under assignment? So pop quiz, no, it's not under assignment, but we'll have to see like how we will put it on web courses. Yeah, we'll make an announcement for that. Okay, question from Victor. Max pooling, the number of parameters 0 is always true. Yes, of course. So it's 0. You don't need any parameters for max pooling. Question from Brandon. Can you use a library for Gaussian for PA? Yeah, I mean, if you just want to use a library to get the Gaussian kernel, yes. But the Gaussian filtering, you'll have to write the code yourself. I mean, you can't just use Gaussian filtering because that will be just one-liner code if you do that. So Brandon, is it clear? Was that your question? Okay, great. So question from Russia. Today I could not see the quiz. I mean, the slides are not visible, or I don't get it. So Ruchia, the slides were not visible to you?
Professor, no, I'm talking, I mean, in the slide I could see the question, but is there any separate quiz created for it?
You mean like on web courses?
No, I mean, like where you could enter the answers or something.
Yeah, you just put like on the chat, right?
Okay, okay. In the
Oh,
chat.
this is like your first time. Okay.
Yeah, yeah.
Yeah, don't worry. Don't worry. From next time you can do that.
Okay, fine. I got it. Okay. Thank you.
Okay, so probably you might have missed like previous quizzes. So for the quiz, it's like you just type your answer in the chat box and send me as a direct message. All right, so any more questions, just let me know, drop me an email, and I think we can end it here. Thank you. Bye.